In this video, I'll be introducing inductive reactance, which is covered in chapter 33.8 of the textbook. Okay, so the last video we looked at a capacitor in an AC circuit. In this video, we're going to look at an inductor. Remember, inductor is really just a coil or a solenoid in an AC circuit. So, take an AC power source, attach it to a coil, an inductor, and of course, just like we can use Kirchhoff's loop rule, and the voltage drop on the inductor has to be equal to the voltage from the AC power source, which means the voltage on the inductor as a function of time has to be whatever the max voltage is times sine omega t. So in the inductor, well, we know from the definition of inductance, then the voltage has to be the self-inductance times the time derivative, di dt. So we want to solve this for the current I, so we actually have to integrate. So when we integrate, we get the current as a function of time as the maximum voltage over omega L times sine omega t minus pi over 2. Well, and actually we integrate, and that, well, the integral of a sine is a cosine, or you can write that as a sine shifted by pi over 2 or 90 degrees. So, similar to what we had for the capacitor, so the voltage and the current do not peak at the same time, like they did with the resistor. So here it's actually the voltage hits a peak first, and then a quarter of a period later the current hits a peak. So they're said to be out of phase, and the current lags the voltage by pi over 2. So now, just like we did with capacitors, we can also define inductive reactance. So remember, we want an equation similar to what we had for Ohm's law for resistors, and we can define the maximum current is the maximum voltage divided by X sub L, where now X sub L is the inductive reactance. And inductive reactance we define as the angular frequency omega times the self-inductance L. And again, you can work out the units, and it works out that it actually has units of ohms. And again, the thing to point out here is that the inductive reactance is directly proportional to the frequency omega. So as the frequency gets larger, the inductive reactance gets larger. If the frequency is small, then the inductive reactance is small. So basically, as omega goes to 0, then the inductive reactance goes to 0, and your inductor just behaves like a wire.